Welcome back to OCR MEI Further Mathematics Speak. Today we're doing chapter 4.5, Inverse Matrix. So when we are doing inverse matrix, there are a lot of steps that you need to know in order to carry out that manipulation. However, I'd like to use a kind of mnemonics method. I'll call this the do D maths method, because the D, the T, and the M are the three steps that you need to use to find the determinant. Not determinant, but the inverse of the matrix. The fact is that the inverse of a matrix is often used to do matrix division, because multiplying by an inverse gives you so if I have A and inverse A, if I multiply both of them together in either order, I'll get the identity matrix, as you would expect, just like normal numbers. Yeah, so let's have a look at finding the inverse. So for a matrix, let's arbitrarily make one up. I'll use 3 by 3 because that's a lot harder to do. This whole do the math method also works with 2 by 2s. So let's first of all write down do the maths. So what is the D mean? D stands for determinants. And so if I have a matrix 1, 3, 2, 0, 1, 3, 2, 1, minus 1. This is just a random matrix. I do not know if it's gonna look well or not. Who cares, really? So I've got a determinant here. We need to find. So for determinants, you can use that 2 by 2 determinant method, or the cross product method, whatever you want to call it. I'm gonna use the same, except I'm gonna use this row instead. Column rather. I'm gonna use this column, and I'm gonna use the 2 by 2 on the right. It still works, but for ones who just started, I recommend just using the top row. The reason I'm using a column-wise method to find the determinant is because I've got a 0 here that can save me one operation, so I'm gonna do that. So I have 1 times the determinant. So 1 times the determinant of here is minus 1, take 3, plus 0. Actually, this is subtract by 0, but you know, for completeness sake, I'm going to do the negative just to remind you of that. Then I add a 2, then the determinant of this 2 by 2 is 2 times 3 times 3 is 9. Take away 2 times 1, which is 2. So with that, we have minus 4 at 14, which gives us the determinant plus 10. For a this determinant, we found this, but what this eventually would become is the coefficient of the inverse matrix. So if I call this matrix M, okay, so let's see, I'm gonna run out of space, aren't I? Let's try this. M inverse, denoted by the power minus 1, is equal to 1 on determinant with a something, I'm pretty sure it's called the adjoint. I'm gonna check my notes actually. I did not write it down. Anyway. Right, this mess doesn't matter. I'll call this the adjoint. So, what is, well, first of all, we've got this coefficient determinant. Then we also need to find 9 lots of determinants. So let's try that. So it's the terminology is gonna get a bit haywire, but I hope you can try to understand. Let's see, I'm gonna use some color in order to help. So if I have position A, position B, position C, D, E, and F, G, H, and I. So I've got these values. So you might ask, why the colors? Well, in order to find each of these, we need to use the minor matrix of these locations. So the minor, if I take A, then I just highlight the position A, then the minor of the matrix is this 2 by 2. So cancel the column and cancel the row, you get the minor. Yeah, these terminology sucks, I know. The value of A is determined not by this original location, but just the determinant of the minor. So the determinant of the minor, as we have discussed, is minus 4, so A should take the value of minus 4. Yeah. Now look at B. So for B we have 3, and we have the minor 0, 3 to minus 1. So let's find a determinant of 0, 3, 0, 3 to minus 1. That one is 0, minus 6, so it's negative 6. For this time, again, it's literally just the determinant of the minor matrix. I do not care about the do not care about the grid pattern of plus and minuses. Do not care about like the cross product, whatever. Don't care about the original value 3. Ignore all that. I'm just gonna take the determinant of the minor matrix. Then 2, I take the determinant of 0, 1, 2, 1. That's 0. That's minus 2. So I've got just minus 2, etc. We keep doing this. 0. We have 3. Minus 1, 1, 2. So 3 times minus 1 is minus 3. Take 2 minus 5. Then we have 1, which is just the outer corners. 1 times minus 1. Take 4 is minus 5 again. Then we have 3. So 1 times 1 is 1, take away 6 is minus 5 yet again. This is coincidental, by the way, I didn't plan this out. 2, we've got 3 is 9, take 2 is 7. For 1, we have 1 times 3, take 0 is 3. And finally, we have minus 1 here. This is just 1, take 0. So we've got this matrix, not quite the adjoint, or it might actually call. There are a lot of terminologies. I might have mixed some of them up. Doesn't matter if you know the names, as long as you know how to do them. So find this matrix that is kind of, I would call this the 2 by 2 determinants matrix. Let's just call it that. 2 by 2 that matrix. With this, we have done the first D, do the math D. So we've got the determinants. Let's see, let me... Oh, that's my bad. Oh dear, I am crap at this. Anyway, now we've done all determinants. Let's try the V. So to do the T, T means transpose. I might have told you what a transpose is, but I can't quite remember, so I am gonna do it again. So to transpose the 2 by 2 determinant matrix, you take the reflection along the identity matrix line. So the diagonal from row 1, column 1, row 2, column 2, row 3, column 3. You keep those the same, but then you reflect everything. So after transpose, denoted by a small t on top, by the way, you get a 3 by 3 matrix, minus 4, minus 5, 7, minus 6, minus 5, 3, minus 2, minus 5, 1. Have a look, see it for yourself what happened. It's actually not that complicated. Transposing is used a lot in matrices, and it's used in vectors as well. Now we got that sorted. Actually, this color code is crap, it doesn't matter. So I've got this transpose done. Now let's do the actual maths, which is just minus sign. So it's the minus sign, which means that you multiply everything here in the grid minus pattern. So if I were to multiply a negative on the grid, then I would have a negative of a negative, negative of negative, negative of negative, and positive turns negative. This is the adjoint, which translates back into this whole thing. And so the determinant, not the determinant, I keep saying this, the inverse of m is actually 1 on 10. Don't forget this, that. I'm gonna actually need to do a bit of highlighting, aren't I? Cut this off just to prevent confusion. 1 on 10 within minus 4, 5, 7, 6, minus 5, minus 3, minus 2, 5, 1. And yeah, this whole matrix in this factorized form is the inverse matrix m to the minus 1. It's complicated, but as you practice it gets easier. The 2x2 ones works as well. You also find the determinant, which is these two. Well, we know how to find the determinant of a 2x2. Then we transpose the 2x2, so you flip the 0 and the 3. Then you take the minus sign, which are on the 0 and the minus 3. Simple, isn't it? Minus 3, did I say? I mean 0 and 3. Anyway, I've dwelled on this too long. It's time to actually get on with some tips. Then I'm gonna make you do a bit of matrix inverse. Similar to the determinants, inverse matrix has its own product relation. If I have matrix M and matrix N, all to the power minus 1, what I would get is not n to the minus 1, n to the minus 1. It's rather n to the minus 1, m to the minus 1. So it's flipped. This is because of some property to do with transposing a product matrix. Because to find the inverse, you did do a transpose operation. The details I will not discuss here because it gets quite complicated, and to show that in general form you need to use something called the suffix notation, which I am not going to torture you guys through. It's going to get too complicated for A-level purposes, and although it's nice to know, if you're keen, go online and look for things to do with suffix notations for matrices, but in general do not actually, like, unless you're doing science at uni, doing math at uni, do not use suffix notation. It's not worth it. And yeah, basically just get on with normal algebra and math and you should be fine for this purpose. So inverse matrix almost always shows up. I say this because I'm not willing to take the chances that they decided not to put a 3x3 inverse into the exam. I'm pretty confident it's going to show up, so if you can do them, then you get some free marks. It is used to solve 3D simultaneous equations. I am gonna come back to this because remember back during factors, I deliberately skipped the geometry of a converging point from 3 different planes. The reason will be discussed next video. For now, this is just a point to make you know how to do the inverse. So question time. We have 2 matrices for you to deal with. Find the inverse of these 2 matrices. I'll give you again, as usual, 5 seconds to get prepared and do the questions before I show you the answer. So I'll show you the answer in 5, 4, 3, 2, 1. The answer is shown here. Make sure when you do the determinants, not determinants, the inverse of a matrix, don't try to expand everything into the bracket, it gets very complicated. Obviously you can do that, but if you leave it in the factorized form, you will get all the marks and it doesn't really matter. So with that said, this is all for this video. I hope you've I hope you've learned something. If you have any question to do with inverse matrices, let me know in the comment section below. I'll try to answer them as well as I could. And as promised, I will do a revisit video on 3 variable simultaneous equations. And yeah, that's all. Thanks for watching, and I will see you on my next one.